Now let's look at some special circumstances for our ball on the string and our car going over a hill here. First, the car. Here is our free body diagram for the car at the top. There's a normal force pushing up and the force of gravity pulling down. And the first thing I want to point out about that FBD is that it must be the case that the normal force is less than the force of gravity. Let's think about why. The common mistake here would be to set those two forces equal to each other, say they're balanced there at the top. But that would be similar to this common mistake we already discussed, in which it's tempting to set these two forces equal to each other for the ball at the bottom of its path. But we know that if those are equal, then the net force is zero and the ball goes in a straight line. It doesn't curve. Likewise, here for our car going over the hill, if those two forces are balanced at the top, then the net force is zero and the acceleration will be zero, and the car will move off to the right in a straight line, sort of flying off the hill instead of continuing to follow that curve downwards. So in order to follow that curve downwards, we need a net force toward the center of the circle. We need a centripetal force, a negative net radial force, to take that velocity and pull it to tilt it downwards to continue to follow the curve of the road. Okay, here are our radial and tangential unit vectors there, r hat and t hat. So if we set up n to l for the radial direction, radial acceleration equals our net radial force over the mass, and our normal force pointing up, that's in our positive radial direction, away from the center of the circle, so plus Fn, and our force of gravity points in towards the center of the circle, so minus mg over m, and then set that equal to minus v squared over r. And then typically this is the equation you would end up rearranging to solve for whatever you wanted to solve for. So we mentioned the possibility of the car kind of flying off the road, and you know from experience that if you go over the hill too fast, you might do just that. Take the hill at a speed that's too great, and the car will launch off the hill instead of continuing to follow this circular curve. So what would cause that to happen? What would change here in our dynamics if you're going too fast? Here are conditions. The car stays in contact with the road as long as there is a normal force. That's your contact force between the car and the road. So as long as that normal force is non-zero, you're touching the road, you haven't gone airborne. But if that normal force disappears, then your tires have lost contact with the road and you are airborne. So we can determine the maximum safe speed for going over the top of the hill without flying off by considering the speed that would cause the normal force to go to zero. The speed at which the tires lose contact with the road, well, that's your maximum safe speed because now you're going airborne. So we take Newton's second law here, and what we do is set that net force to zero, showing that we're losing contact, and if we do that, we're finding the maximum safe speed at the top of the hill. So set that to zero, we see our masses will cancel out here, rearrange to solve for the square root of gr. This expression gives us our maximum safe speed at the top of the hill, where r is the radius of curvature of that particular hill. We have a similar circumstance with our ball on a string here. If you don't swing it fast enough, then as the ball approaches the top of the circle, the string will go slack and the ball will kind of like fall limply downwards instead of staying on the circular path with a taut string. So here's our conditions. The string is taut as long as there's tension in the string, as long as that tension is greater than zero. The string goes slack and the ball falls off its circular path if our tension equals zero, if there's no tension. So the minimum speed you need here at the top in order to swing all the way through the top without the string going slack can be found by taking Newton's second law for the ball at the top of the path, point C, and solving for the speed at which the tension here disappears. The string goes slack if the tension is zero. So if we take this expression and set that tension at the top equal to zero and solve for the speed, that tells us the speed at which the tension disappears. So if you go any slower than this, the tension will disappear even before you get to the top. The string will go slack and the ball will fall off of that path and become a projectile following a parabolic path instead. So set that tension equal to 0 at the top, solve for the minimum speed required to complete the loop at the top, and once again, we find this expression, square root of gr, which happened for slightly different reasons to be also happened to be the max speed for your car at the top of the hill. That's also the minimum required speed for the ball at the top. That's the speed it has to have when it gets up here to point C. That concludes the special circumstances, but I wanted to look back at the acceleration vectors that we drew on this picture here. I argued about the directions of those acceleration vectors as pointing in the directions of the net forces, and that's true, but I didn't really get the magnitudes correct here, the relative magnitudes. I've got acceleration at the top looking bigger than acceleration at the bottom. And that's probably not the case, actually. In fact, if we look at the special circumstance where the ball is swinging where the ball is reaching the top with the minimum speed such that the string goes slack at the very top. So if the tension goes to 0 at the very top, it's possible to show that instead of these magnitudes, this is the correct picture. All right, let's see if I can get this on the screen. Okay. If we do a little more work and look at the case in which the tension goes to 0 at the top, it's possible to show that the correct relative magnitudes of your tension vectors are these at these two moments. So these vectors are all drawn to relative scale in this picture. So we have the force of gravity the same at all three moments. We see our velocity vector here, here, and here decreasing as it goes up. So these are correctly drawn to scale relative to each other. And this tension would be double the tension here if our tension goes to 0 at the top. To prove this, we would need to utilize some conservation of energy. So we won't be doing that at the moment. But I just wanted to let you know that these acceleration vectors are not drawn with the correct magnitudes here. I had that wrong. To get the correct magnitudes, we would need to use conservation of energy to work out this picture here. And then we would find that at the bottom, our net force, let's see if this is 6 units up and 1 unit down. Our net force would point inwards there, and that would be the direction of our acceleration at the bottom. Here at the side, once again, we would use the parallelogram method for adding vectors to find that our net force pointed in that direction, drawing the diagonal of your parallelogram, and our acceleration will be in the direction of that net force. So here acceleration is straight up, here it's at that angle, and these are the correct relative sizes. And at the top, our net force is just that force of gravity. So our acceleration would be straight down with that magnitude. So note, I've got the acceleration at the top actually looking like it's about a fifth of the acceleration at the bottom. That's more accurate. But once again, we would need to utilize conservation of energy to prove this. So for the moment, this is just FYI.